Okay, so now we're going to use those laws. Copied out the 4 that are on your formula sheet. So they're at the top of your page. On your formula sheet, they're in the sort of the first third right down. Okay? They use capital M and capital N. Could be any, M could represent a whole monomial, right? It's not just necessarily a number. Okay, so evaluate each of the following. So we're going to try to do these without a calculator. You don't need one for these. Some of these we've already talked about. So when we have an argument of 1, what do we know the log is? 0. When the argument and the base are the same, yep, a 1, exactly. Okay, the value's 1. Now here, notice how you can figure this out in your head, right? 5 squared is 25, so you know that the value is 2. Now that we've learned the power law, you can think about it this way. 5 squared, 25 is 5 squared. You could show it like that. And that says we could bring the 2 in front, right? And then it would be there, log with the base and the argument the same as 1. 2 times 1 is 2. That's longer. If you know that 5 squared is 25, then you should know the value of the log is 2. Okay? But now that we've learned that power law, you might think about it that way. Same thing here. Right? So 64 is 2 to the 6. So now we know that the value of this is going to be 6. The 6 goes in front. Log of 2 base 2 is 1. Now, this one here, this is a 5 raised to the exponent, where the exponent is a log itself. Now, in this one, we know, we just did, log of 25 base 5 is 2. So this is going to be 5 squared. Oops, which is 25.
That's how you get rid, like when you're solving algebraic, that's how you get rid of logs in the first
Exactly.
Raised to the power.
Yep. So here, think about it. If your base in the exponent and the log are the same, then the answer is the argument. Okay. So here, if the base of the log and the base of the exponent are the same, your answer is the exponent, right? So the argument or the exponent, depending on where you started. Okay. And logs are inverses of exponents. So that gets you back to 25. These are the same here, so that's 64. Sometimes we'll give you ones that aren't like this. You can actually do the whole process in your head. What's the log of 64 base 2 to the whatever, right? But maybe we'll give you 3 to the log of 64 base 3. I don't know what log of 64 base 3 is, but then you know these bases are the same, so the answer is the argument. Okay? So we summarize these. These aren't on your formula sheet, but they're very helpful to know off the top of your head. Argument is 0. Argument is 1. The value is 0. Argument and base are the same. The value is 1. Argument, the base of the argument and the base of the log are the same. So the value is the exponent. Base of the exponent, base of the log are the same, so the value is the argument. Okay. Okay, so these aren't quite as simplified as the previous ones. So what you can do here, if you want to show work, you can think about, okay, that's log base 7. 49 is 7 squared. That's raised to the negative 3. So this is going to be 7 to the negative 6. Base and base are the same, so the answer will be negative 6. If you want to show it, and okay. Now, take a look here. Sometimes you might think, oh, okay, I'm multiplying powers. I should see if the bases are the same, and then I can add the exponents. But the bases here are not the same. So I have to evaluate inside the brackets. Base the same, so the value of the first is 2. Base stays the same, value is 7, so your answer is 14. Okay, true or false in the next table. I'll give you a couple minutes to look at those. Again, common type of question that might be asked on an exam. If you think it's false, then see if you can write a statement that is true that involves those same logs. I don't know. Okay, and then try to come up with statements to make them true. There's a lot of false statements there. So here, we're adding logs with the same base. In this statement, they also added the arguments. What we just learned is that we're adding logs with the same base. We multiply the arguments. So a better statement that's correct would be something like that. Okay. Remember, I showed one like this. Log of 9, yeah, you can show that. The log of 9 is equal to log of 3 squared, but that is different. It is not equal to log of 3 all squared. Okay? Try it on your calculator. Come on. So go log of 9. Okay, then go bracket log of 3. Go brackets squared, and you get a different value. Okay? So be careful. Same thing here. This is dividing. They've obviously divided the arguments. Remember, when do you divide the arguments? When you're subtracting logs with the same base. So a better one here would be that. Okay. Next one would be something to do with change of base. So check, it is true, because we're taking the log of x, so the argument of our single log is the same as the argument of the numerator. And the base of our single log is the argument of our denominator, and we've changed the base. So that is correct. This one is a common mistake, but remember that exponent is only on B. It is not on A. There are no brackets around that. So this x I cannot bring out front. Okay, it is only on B, not on the whole thing. So what you could do here is split up using the product rule. Okay, so split up the two factors, and then bring the, if you want to bring the x down using the power law, you could show it like that. Okay, Gloria? How do you
How would the identity changes from the log EX to log EX?
In terms of an identity, well, this is actually given as an identity for you. Right? So we wouldn't need to, you're not going to need to go into more than that. But probably what I'm doing is like you take the raise each side to the exponent. Yeah. You take, I would say, take left side base 3, raise it to that exponent. Right side base 3, raise it to that exponent, and try to simplify it. But it's kind of confusing. Because it is a law, an identity here, you wouldn't have to explain that.
One of those fundamentals.
Okay, so use the change of base law to evaluate this without a calculator. So now we're using that law there without a calculator. Now, you are going to have a calculator, obviously. So then you would, we or they, the diploma exam writers, would make it so there's some unknown in it, right? So you can't just punch it all into your calculator. In any case, to evaluate this, you want to look at these, right? I can't express 27 with a base of 9, but I could express both with a base of 3. So that would be what I'd want to change my base to. So change it to the lowest of these two, or even smaller, if I can express 27 with a base of 9. I know the answer is going to be negative, right? Because this is greater than 1 and this is a fraction. But here, change of base, you make a fraction with your new base. Your numerator argument is the original argument. Your denominator argument is the original base. Now, what do I raise 3 to get 1 over 27? It's got to be negative 3. Okay. If you wanted to split this up, you could into subtraction, log of 1 base 3 minus log of 27 base 3. But hopefully, you can do that in your head.
Or you can also, like, where
yeah, or the power law, yeah, you can show this is 27 to the negative 1, then bring that down. Okay, or you can just think about what do I do to 3 to get 1 over 27? The numbers aren't too big here, so you should be able to do that. So that's your answer. And you can check it with your calculator on your own time. Okay, so then we have a couple of multiple choice questions. Multiple choice questions are interesting for logs because there are different ways of showing a log, still in simplified form. So sometimes in a multiple choice question, it will say, what is the choice or whatever that does not work, right? So 3 out of the 4 will work, because they can be shown in slightly different ways. Like log of 64 base 8 is the same as log of 60 log of 16 base 4. They're the same value. So you can't show it in different ways. So we're trying to express this in a different way. Which way works? In this case, there's only one correct. Now, in the old days, when no one had the ability to do a different base other than 10, you would have to do a log base. You could evaluate all of them, but you have to do that log base 10 in your calculator. So let's try not to just go through and check the answers. Let's see what makes sense here. So let's take a look at our possible answers. This is base 10, base 5, base 10, base 5, right? So obviously, we're either changing that to base 5 or base 10 based on these answers. Because the argument is 25, I'm thinking it's base 5 makes sense, right? So let's express that using change of base with base 5. So the argument in the numerator would be 25, and the denominator would be 3. Now this, it has a value of 2. I don't know what the value of this is. So now I look, which one is exactly the same? This one. This one's close, but that's base 10 actually. Right? So that's not going to help you. Sometimes you want to look at the actual answers, and that might give you a faster way to get to what you're looking for, what they're looking for. Okay, so now the next one, we've got a log equation there. It says convert to exponential form. Try to do that swoopy swoop, but there's a coefficient. You can only do that 2 arrows that I call swoopy swoop if this is not there, right? So, a couple of choices. You could divide both sides by 3/4, or you can use the power law to show that exponent of 3/4 on x. Okay, either one works. So I'm going to look, because it's a multiple choice, let's think about what we're actually looking for, because there's different ways of showing it. So this has, none of them is just x equals, right? This is 3/4 x, this is x cubed, x to the 3/4. So not just x equals. If I were to divide this by 3/4, let's do it. So that would be end up being 20/3. Okay, when I multiply both sides by 4/3. Then I would have x equals 7 to the 20/3. Sorry, yeah, 20/3. Well, I don't have that there, right? So again, you can go through and evaluate, but none of those are in the form x equals. So that was when I got rid of the 3/4. So let's try the other method that I mentioned, now that we know the power law. So I'm going to show that as log base 7 of x to the 3/4 equals 5. Now if I do my swoop, I get 7 to the 5th equals x to the 3/4. There it is. So when you're simplifying and working with logs, a little bit different order you might have than your neighbor. Doesn't necessarily mean that it's wrong. You could do it in a different way. In this case, it depended on what form the answer was given. It wasn't actually given in the form x equals. So that's not the final solution, right? But it's one step towards it. Okay, question 7. Try those without a calculator using the new laws. So this is subtracting and adding, subtracting and adding combined. prime example of why you'd want to know these laws, because separately, without a calculator, I don't know what that value is. I don't know what that value is. But it's a subtraction, so I can show it as a quotient that simplifies to 1 over 16. So now, with a base of 4, 16 is 4 squared. It's now in the denominator, so it's a negative 2.
Kind of like using, when you get the trig identities, where like, you might not have an exact value solution, but you can make it into multiple exact values.
Yeah. Yeah. Okay, remember, log without a little base is base 10 for common logarithm. So when we're adding logs with the same base, we multiply the arguments. Root 5 times root 2 is root 10. Root 10 is the same as 10 to the exponent 1/2. And so, same base in both, so it's going to be equal to the exponent. Got more than one term here, so this will be log base 6. So 20 divided by 5 times 9. That looks like decimal. I'm just going to fix that. And again, I think in log, some of you just have to work on your handwriting, not even the math, right? Try to make sure that that little 6 looks different from the 36. Okay, so dealing with a lot of numbers, now in question 8. It says express each of the following as a single log and state all values of the variable for which it is defined. So we have to remember what types of numbers we can have in a logarithm. Can we take the log of a negative number? No. So here, x has to be greater than 5. Here, x has to be greater than negative 1. Okay? Kind of have to think about which one wins. So if you were to draw a number line, so greater than 5 is this way, greater than negative 1 is this. So if I made my statement that this is true for x greater than negative 1 because it covers more numbers, would that be correct? What about if I chose 0?
Break everything.
Whatever x value you choose has to work in the whole thing. So 0 would be fine here, but not fine here. So you want to, when you look at your two separate terms, look at where they overlap. That's the domain for the whole thing. And you always need to go back to your first, whatever was given to you. Because that could be shown, obviously we're supposed to simplify it, so let's do that. It can be shown like that, which we could expand out and show it like that. Okay. Now, if the question I gave you was just this, then what would it be defined for? So think about the parabola in that case, or 5, negative 1. So that would be a parabola opening up. Okay. We want the x values that give positive y values in this case. This is y equals this. So that would be x less than negative 1, x greater than 5. That's different than just this. So it depends on what you start with. Because if I said this was true, then that's saying, okay, if x is -2, it works. Well, yeah, if it was, this was my original, if I put -2 in there, I get 4 plus 8 is 12 minus 5 is 7. But if I put -2 in here, that doesn't work. Here, that doesn't work. So you need to go back, just like a rational equation or expression, you go back to your first factored form. You don't go and look at just the answer. Because if you look at just the answer, you've eliminated some of the possible or introduced more or whatever. So this is the correct simplified form, but our domain is defined where x is greater than 5. Okay, so just think about that. Always go back to the original. So this is a subtraction, same base. So this will be log base 3 of x squared minus 2x minus 8 over x minus 4. You can factor the numerator. Okay. Now, think about what this is defined for. So this was our original. So this is going back to Math 20 to look at these inequalities, right? So that's 4 and -2. So that's x squared, y equals x squared minus 2x minus 8. We want that to be greater than 0. So that would be for x less than -2, x greater than 4 for that one. This is obviously x greater than 4. Okay, so where do they overlap? Just at the x greater than 4. If I include this, then that's saying let's choose a value like -3. If I put -3 in here, it's going to be okay, but if I put it in here, it's not going to be okay. And just one other thing I want to show you on this one is maybe you decide, oh, I'm going to factor that right away. Okay, so I factored it, then I think, oh, okay, I can split that up. And then when I split that up, it goes out to 0, and I get that answer. Right? So, again, you might have done it that way, I might have done it this way, still get the same answer. Still, for your domain, look back to the original question. Okay, next one, question 9, turn over. Again, evaluate without a calculator. Okay, so maybe you can, hopefully you can do that in your head. So this is log of 1/2 base 8. This is log of 2 base 8. 2 is smaller than 8. So to get it to be smaller, it's got to be a root of some kind. What root of 8 gives you 2? Cube root, yeah. Okay. So cube root is the same exponent of 1/3. This is a fraction, so this is going to be a negative 1/3. This will be positive 1/3.
here are negative 1 over 2 per negative 4 negative 3 and then
Say it louder. Say it louder.
if you like raise 1 over 2 to the power of negative 4 and raise 3 to the power of 2 and then
Yep, that's another method. So here, you could go, okay, I'm going to bring that negative 4 as an exponent. Bring the 2 as an exponent. So really, that log of, that's going to flip it, and 2 to the 4th is 16. And then that's going to be, okay, now saying that, you're going to, in this case, in order to get it to be, you can't just use a whole number exponent to get 16. So this, you can think, okay, well, cubed root of 8 is 2. 2 to the 4th is 16. So you can go 2 to the 4 thirds. Sorry, you can just do 4 thirds. I did the 2 in my head. So that is 4 thirds. And then same thing here. Cubed root of 8 is 2 squared. So that would be 2 thirds. And then that'll give you 2. You could also use the change of base. If you wanted to make this log of 16 base 2 or log of 8 base 2, you get 4 thirds. So, yep. Oh, yeah, and then you can do that. Yep, that would be easier for sure. Okay, so there's a variety of ways. Okay, so then getting to some ones again that don't have numbers, so that we know you're not just plugging it into your calculator. So there's an expression. Write it as a single log. It's a multiple choice answer there. Remember, we don't like coefficients. Really, when we're adding or subtracting. When in doubt, the answer is C. Okay, so adding logs with the same base, you multiply the arguments together. Okay, that C does not go on the whole product of X and Y, just on Y. Okay, again, another multiple choice. Now we're going to the expanded form, making it less simple. So that's a quotient, anytime you see a fraction. So think about what that is split up into. Looks like you're at a horse race. Okay, so that's my first step that I do. Numerator, denominator. I don't see my answer there. Then think, oh, well, that's a product in itself. And actually, I can evaluate log of 27 is 3.
David, this one.
Oh, did I? Oh, yeah, I did. Okay, let's do 12. Let me go back, sorry. Or maybe I'll just leave 11 for you to do because we're running out of time. So we'll just go to 12 here. Now, be careful. We're subtracting whatever this is. So I'm going to open a set of brackets. Right? Because that alone, log of m times n, is log of m plus log of n. Okay, so yes, they're added together, but I'm subtracting everything here. So there are some brackets here, but that's 3 multiplied, so that's not going to work. If I get rid of the brackets, then can I find it? Subtract and subtract. Okay? So be careful on that. Okay, try 13. Again, no numbers, so you have to know your log loss. So this is a definition statement. We're saying log of a base b equals m. If that's true, try to express this in terms of m. So basically, I want to try to get log of a out of this. Okay, well, I've got log of 1 over a squared right now. So we could, there's a few ways of doing it. Maybe I show this with a negative exponent. Okay. 1 over a squared is the same as a to the negative 2. Then, some people right now will tell me that that's m to the negative 2 as my answer. Because they just see this part and they think, oh, I'm just going to put m in there, raised to the negative 2. That negative 2 only goes to the a, not to the whole log. So using my power law, it's going to be negative 2 log base b of a. Now I can substitute m in there. You could also do log of 1 minus log of a squared. Okay. And then use the power law there. Log of 1 is 0. So you can do that. Take a look at 14. Again, different ways of doing it. When I look at 14, you might think, algebra. Are there some like terms I can collect before I do anything with logs? There's log of a, there's log of b, and no other variables. So you can start dealing with maybe using your power law for all of these and collecting them. Or you might want to collect like terms. So for example, if I get rid of the brackets, okay, that just becomes adding. Then I've got like terms. It's like back to math 10, math 9, or whatever. And you have like terms, and you circle, underline. 2 log a minus 4 log a is negative 2 log a. Negative a half log b plus 3 half log b is just 1 log b, which is log b. Can't use the product law or the quotient law yet because of this too. So what I like to do is use the power law to get it back up into the exponent. Okay. Or you can leave the negative out front if you wanted to. But now if I'm adding these, the coefficients are 1, then it's the product of those. And we like to use positive exponents. Okay, we'll do one more, and then you can do the last two on your own. Last three on your own. Then the exercises. Okay, so 3 to the x equals 4. Obviously, x is not a nice number, right? It's undecimal. So don't figure out what it is. You just want to express log of 16 base 3 in terms of x. Okay, so that's a log, that's an exponent, right? So maybe what you want to do, there's different ways of doing this, but you could either say, that's 4 and that's 16, so I could show that with as 4 squared. Maybe that's going to help. I could show this in logarithmic form, right? Log of 4 base 3 equals x, if x 3 to the x equals 4. That to me makes it easy, right? Now, this I can show as log of 4 squared base 3. Power log, and then substitute. So you do 16, 17, 18, and then the exercises. And there is some textbook. Notice today it also says proving log identities. We don't have time for that. We'll do that at the beginning of tomorrow's. Okay? It's not the same extent as trig identities. Yeah. I thought oh, did I?